So in this slideshow, I'm going to discuss complex numbers. This is section 6.5 in your Larson Pre-Calc book. So I want to remind you there are many number systems, and I don't have all listed here, but integers, we often use a capital Z when you see me denote that on the board. Z for German Zahl, the word for number. So integers are those negative numbers, negative 1, 2, 3, 4, 5, 6, also the positives and include 0. And if we go to a bigger number set, the rational numbers are the set of all numbers that can be written as a ratio of two integers. So you'll see we use a Q for rational numbers, and it is the set of all numbers that you can write as a fraction. So 1/2, 3/4. Now, even if it's a decimal, most decimals can be written as fractions. You know that for 1/3 is 0.33333. Many other, if you have a pattern with repetition, like 0.123, 0.123, well, that's 123 over 999. So we've talked about some tricks like that. Remember, rational numbers was a set of numbers. Numbers that would not be rational would include pi, e, square root of 2. So if we include those numbers, we have what we call the real numbers, so the set of real numbers. Now, it took many, many years for mathematicians to admit that there were numbers beyond that set worth working with. When they finally allowed I, which I think I've talked to you about a story, very interesting, but I'll try to stay on topic for this video. When they finally allowed I, then what we have is a set of complex numbers. These are the set of numbers that can be written as a sum or a difference, so as a combination, a linear combination of two, you'll see A and B are real numbers. So this is a complex number, this entity, where it has a real part, A, you'll see it's purely real, and B is a real number. It is called the imaginary part, so B is the imaginary part. It is multiplied by I, which I represents the square root of -1. And we have worked with this some before in college algebra, so we'll be focusing on these ideas and relating it to trigonometry, but I did want to remind you of those set of numbers. So we are about to talk about the set of complex numbers. Remember, I use a capital C to denote that set. And something kind of funny I wanted to tell you about, I maybe have told you this story about one of our former principals wearing a t-shirt that had this as its screen printed on the front, and we got an angry call from someone in town saying, how dare we try to teach our students that I is less than 3 pi. It has no weight. It's not less than or greater than anything, and that's totally true. That poor gentleman didn't understand that this was intended to be kind of a pun, like this was a heart. But I just wanted to mention this. So it got this bad name as an imaginary number, but that doesn't mean that we don't use this. We use this very frequently. So engineers use I, differential equations we use this value, but or this expression. But this is not a number in real sense. So there's nothing that you could equate with it. 3i is not greater than 2i, or 4i is not bigger or smaller than another pure imaginary number. So keep that in mind. I just wanted to remind you of that. What I want to get you thinking about with that story is that we do have to find some type of ordering. Like, how are we going to organize all of these if we don't have an ordering as we do with the real numbers? And we will look at that in just a minute with graphing. So first of all, I want to remind you of powers of I. So I, remember, is the square root of -1. If you square both sides of that, so I squared is equal to -1. If you multiply by I again, then I cubed would be -I. I to the fourth multiplying by I again would be 1. And you'll notice if I continued this pattern, I kind of get some repetition. So multiplying by I again, I have I, multiplying by I again, -1, multiplying by I again, etc. So it seems like I to any power, and you could play with this longer, we will always get one of these 4 outcomes. I, -1, -I, or 1. And that's totally true. Sometimes you'll have questions, maybe you'll have to simplify I to the 17th degree. Well, remember that you'll have one of these four cases. So whatever that exponent is, write it in terms of, so mod 4 if you're familiar with that. But maybe write it, think about, okay, how many times does 4 go into that number and what would be my remainder? Is it 1, 2, 3, or is it divisible by 4? If the number is divisible by 4, so if the power is divisible by 4, then I to that power will simply be 1. If you have a remainder, then it will break into one of these three cases, 1, 2, or 3. So, for example, I to the 235th degree. Well, that would maybe appear on some type of a standardized test to be confusing, but really it's not a big deal. 235 is 232 times plus 3. So you'll notice I've written this I to a power times I to the power. Exponent rules say that we would add those to get 235. The reason I separated this is because 4 obviously goes into 232. And you would have 3 remainder. Well, I cubed is negative I, and so that would be your third case here. So anytime you see those, that's how you simplify those. They're really a piece of cake. So a complex number can be expressed in, so we have this form. I want to mention we often use x's and y's when we work in algebra, and that is because of where that mathematics began, but we often use z's and omegas or w's for complex number, so equations with complex numbers. So you'll often see me use a z pretty much on this whole slideshow. If z is equal to, so expressed in its real and imaginary form, remember that the real part, often we might use re of z, that is the whatever that value a is. The imaginary part is not IB, the imaginary part is just B, but that is the number times I, so whatever is times I. Remember, B is a real number, but so the imaginary part is a real number itself. A little bit of notation, if you put a little line over it, it kind of looks like vector notation, but it's not quite. So it's like Z with a little bar over it. Z bar represents the complex conjugate. From algebra, I believe that I used that notation in college algebra as well. If you don't remember, that the complex conjugate is the number changing the operation there. So if you had 3 plus 2i, then its conjugate would be 3 minus 2i. And we actually have some properties with the conjugate, so I'll talk about those a little bit in just a little bit. Another vocabulary word, modulus. The modulus, you can think of that as the absolute value. I'll show you a picture in a minute why that is, but when we graph this, it will make total sense if you think about right triangles. The modulus, the absolute value, what you do is you take the square root and you simply take the real part squared plus the imaginary part squared. So these are two vocabulary words that I will use in these slides. You will see in the book. The complex conjugate has z bar and modulus, so it's really just the absolute value of z is equal to this. I'm not sure your book actually uses the word modulus, but the modulus just refers to the absolute value, like magnitude with a vector. So very similar. All right, earlier I was discussing I is less than 3 pi, and I needed to set you up a little bit about the real and imaginary part. I mentioned that we have no ordering, so that could leave everything very, very disorganized. However, what we do is, because a complex number is formed, it's the linear combination of two real numbers, then we use our old x-axis to represent the real part and the old y-axis to represent the imaginary part. This allows us to organize our complex numbers. So we're going to practice graphing a few. If we needed to graph 3 minus 2i, so what is different about this is usually you graph a number, it's purely real, so you have a two-dimensional axis that can represent many different numbers. What I'm getting at here is a two-dimensional, or a complex number needs the whole 2D plane. So 3 minus 2i, the real part would be 3, the imaginary part would be negative 2. So we're going to go out 3 along from the origin and down 2 so that we are in quadrant 2. I'm sorry, quadrant 4. So this would be A. Point B, the real part is negative 7. We'll go to the left of the origin, negative 7, and we would go down negative 12, so that B would be in quadrant 3. Now see, I tried to confuse you. The real part is -2. The imaginary part would be 1. And so -2 will go to the left 2 and up 1. This will be in quadrant 2. And to get in quadrant 1, your real and imaginary part, you would both have positive signs for that. Now I want to remind you of operations. This would be from college algebra. When you add two numbers that are complex, you just add the like terms. So if they're purely real, add the purely real parts. If they're imaginary, B and D, then you'll add those terms together. And that's really all there is. If we had actual constants, we could combine those. That doesn't get a lot easier with the trig form. It actually might even seem more complicated. So this is going to be how you would add numbers in, even in our section 6.5 using trig form. If you'll recall, for multiplication, so if I take a plus ib times c plus id, we did this in college algebra. You can think about distributing this out, so foiling, and then by combining like terms, so I have a negative here when I get ib times id. That I squared, remember, is -1, so that's where this negative comes from. Your real part would be ac minus bd. Your imaginary part would be bc plus ad. A couple properties I want to remind you of. So remember, these are conjugate pairs, so z and z bar. If you multiply conjugate pairs, the imaginary part completely cancels. And so if you were to take these just and multiply those out, so you'll have a squared, then you'll have a plus b squared. The I terms will completely cancel so that you just get a squared plus b squared. If you'll recall earlier, I talked about the modulus, and it does have a square root. So this is actually the modulus squared. This is a property. Z times z bar is equal to the modulus squared for any complex conjugates. That's actually useful. If you recall from algebra, when you have a complex number in the denominator, it's kind of seen as improper, kind of like when we put radicals in the bottom. Doesn't necessarily mean it's not, and it's still the same number, but to what we call simplify that, or to rewrite it, you can multiply the top and bottom by the conjugate. Doing so will cancel the I in the denominator. You'll have the modulus squared, so that you have 1 over z is equal to z bar over the modulus squared. That will only come handy if you try to do a couple of the proofs in this section, but it's something I wanted to remind you of. We did work those in college algebra. Alright, so we've practiced graphing, and now you might be wondering, well, why are we doing this in trig? I haven't done anything trig related. Totally true. That number, when I was graphing earlier, so earlier I said z had the form a plus ib. So this horizontal change from the origin to get to that point representing a complex number, the horizontal change is a, the vertical change was b, the modulus represents your distance from the origin, just like with the magnitude when we studied vectors. So I have labeled here the modulus of z. If this angle theta were a reference angle, then a here, the horizontal change, you'll notice that that's the adjacent side, so I could use cosine of theta equals a over the modulus. Well, when you solve for a, you get the modulus of z times cosine of theta. If this is b, then sine of theta equals b over the modulus of z. When you solve for b, you have the modulus of z sine of theta. This is your horizontal change then, and this is your vertical change. If we were given, instead of an actual point, the horizontal and vertical change, but maybe the angle, that's where trig form comes in. And actually this is more frequently called polar form, and that will make more sense once we study polar graphing, which is a little bit later in your book. So the modulus of z, you can think about that as the radius of a circle that would be centered at the origin and going through this point right here. So the horizontal change, your a, I've substituted that here. Your vertical change, I've substituted that. Since they both have the modulus of z, often we factor that out so that any complex number can be written in the form of the modulus of z times, and this is grouped together, cosine of theta plus I sine of theta. And this works for any complex number. what's very nice about this polar form is it's so much easier to multiply and divide numbers and to find powers, and there are actually really cool formulas that come out of this form. So that's why we're studying this. So we want to practice writing complex numbers in trig form. Here I have z is equal to 4 minus 4i. The modulus of 4 minus 4i, you'll notice I've taken a squared plus b squared. And if you were to draw this, by the way, and I really recommend that, this would be in quadrant 4. If you draw that point and form the reference triangle, well, the hypotenuse has to be 4 square root of 2 because that triangle, you'll have a 45, 45, 90 triangle. Also, if you draw that picture, it will help you find the angle. You can use the fact that, so similarly what we did with vectors, if this is the horizontal change A and this is the vertical change B, and you were given the angle, then tangent of theta is equal to B over A. Tangent of theta is opposite over adjacent. So arctangent of B over A is equal to theta. So what I've used to find this is I've taken B over A, which is -1. I've taken arctangent, and that gives me -pi/4. And when I graph it, that's completely appropriate. It's in quadrant 4. Keep in mind that if you use this and your point lies in quadrant 2 or 3, arctangent will not give you the correct angle. You'll have to add pi to that. So I really recommend graphing these. Students, the most frequently missed problems here are when students don't think about the inverse trig functions, and that's why we spent so long on that. So now that I have the modulus, I simply substitute that. It'll just be out front. And in parentheses here, once you find the angle, you substitute that for both of these. So cosine of the angle plus I sine of the angle. Now, this is all there is to it, and I'm very happy if you leave it in this. Often I'll get some questions. So what else would you ask me in class? Well, you might ask me, instead of writing it with a -pi/4, can I write it with 7pi/4? Totally, those are coterminal. So what you would do is you wouldn't want to leave a -7 over a -pi/4 and a 7pi/4 together, because those really should be the same angle because of this notation. It's just the same angle. So what I did is I changed both of those to 7pi/4. Now some of you might be asking, okay, but cosine of a negative angle is cosine of that angle, and sine of a negative angle, because of the odd property, is negative sine of that. Totally true. This is actually written more in the conjugate form, because this is more of the form a minus ib, if you'll remember what I did before. But it's not a different point, it's actually the same point. So I would recommend just feel comfortable with leaving this totally, but I'm anticipating you might have some questions. So the reason I'm talking about this, there's not one and only one representation that's the same number. So keep that in mind when you show your work. It might look slightly different than the book, or it might look slightly different than someone you're working with. That can be okay. They're probably the same thing. So hopefully we'll talk about graphing these, and that will help you check if you have the same number. Okay, for a different one, z2 is equal to 5i plus 12. Two things you need to find to write it in trig form or polar form. Find the modulus. Simply use Pythagorean theorem. That's a Pythagorean triple, 5, 12, 13. Arctangent, you don't have that memorized, so you would need to use a calculator. Make sure you're using the appropriate quadrant. If you graph this, this does lie in quadrant 1, so this is what I had from a calculator in radians. I simply substitute the modulus out front, substitute the value, and you're done. You might ask me, well, can I use degrees? Totally. You would just plug in the degree value here. And that's really all there is to it. If I say leave it in polar form, leave it just like this. In the textbook, if they do something different, they might type 13 cosine of this value in the calculator, and that would be your A, and then they'll type 13 sine into the calculator, and that would be your B. You will get 5 for, actually, you'll get 5 for the sine times 13, and 12 for this 13 cosine. Keep in mind, I think that this one was tricking you a little. So notice that I did arctangent of b over a. And I was a little nervous I did that wrong. It's always arctangent of b over a. This is written back in the bi plus a form. So notice that I had to do b over a. Graph this, and you'll notice the along the x-axis you go at 12 and then you'll go up 5. So that's why I had to use b over a here. For I, so z3 equals I, first put it in polar, or first find the modulus. The absolute value is just 1. If you graph this, it's just the point 0, 1 in the Cartesian plane. The angle would of course be pi over 2. It's on the positive y-axis. So plugging those values in, you have cosine of pi over 2 plus I sine of pi over 2. These are almost so easy they might be seem difficult, but these are a piece of cake. The absolute value of -1 is obviously 1, so modulus will be 1. And if you were to graph that, that would be on the negative x-axis, so the angle on the unit circle you would think of pi. Plug those values in and you have it. This one's actually a really important one that I want to bring up, and I'll talk about in another form. So there are totally other forms to write complex numbers in. I will try to stay on topic. Today we're trying to focus on trig form or polar form, but I want to go over this vocabulary. If you see something and it says to write a complex number in rectangular form, that is the a plus ib form. We've worked with that in college algebra. Trig or polar form, it would really more than likely be called polar form, is the form that we have just been discussing. In algebra, I believe I've shown you this, but it won't truly probably make sense until you've learned a little bit more calculus. But e to the I theta is equal to, completely equal to, cosine of theta plus I sine of theta. Because of that, this portion can be written as e to the I theta, and this is exponential form. This is actually the polar form, or this exponential form. That would be how I would work with complex numbers if I were working with them. It's more general form, so I would use that in complex analysis, I would use that in calculus, I would use that in differential equations. So if I'm going to try to include this on many of my slides. If you want to write all of your complex numbers in this form or this form, when you're asked to do it in polar form, both work for me. I hope that you feel comfortable with both. You can choose which one you want to answer your quiz questions in. They're the exact same thing. You might also think of these as ordered pairs. So when I graph a complex number like 3 plus 2i, well, it's in the same position as when x is equal to 3 and y is equal to 2. Actually, a lot of old books, if you pick up an old complex analysis book, so newer books would use this form, older books would use this form. They just write a complex number and it looks just like an ordered pair, or it looks just like a vector. And so if you had parenthesis 3 comma 2 parenthesis, that's representing a complex number. Vectors, when we put bracket 3 comma 2 bracket, exact same idea. The ij from vectors, not the same I. So that's why this sometimes gets confusing. In a trig book, they're normally back-to-back sections, but don't let that confuse you. The I hat is the unit vector. This I is the square root of -1. So be careful with that. You can actually represent complex numbers as matrices as well. If you're a programmer, then this would be something you might use to create a program that will draw the Mandelbrot set, so something like that. So matrices, the properties are actually the same. I'll try to stay on topic right now, but you can actually see this in maybe a linear algebra class, or if you go to program and do something with complex numbers. So just FYI, complex numbers can be written in this form. If a were 3, you'd have 3 down the main diagonal, and if b were 2, you'd have a -2 here and a +2 here. So these are just these are 5 different forms, and all the properties for complex numbers are actually the same in the field of complex numbers, but again, I'm going to try to focus on just these 2 forms right now. So I do want to go over, well, exponential form, it seems so much easier to work with, and totally true. Earlier I wrote these numbers, so 4 minus 4i, I wrote those in the trigonometric form. In exponential form, you still find the modulus, you plug that in, and you find the angle, so theta times I theta, you plug that in, and you're done. That's all there is to it. So that's why I'm saying if you want to do this with your work, instead of the trig form, completely identical, same information. Here I plugged in the radian value. I plugged in pi over 2, and the last one, Now this one's special, so I plugged in the modulus is 1. So if you have e to something and the 1 is out front, then that means the absolute value is 1. And I plugged in the angle pi. So this says that e to the pi I is equal to -1. And if you haven't seen that before, that's actually a really well-known identity in mathematics, incorrectly called Euler's equation. So e to the pi I is equal to -1. You'll see I've put them on the same side right here. This formula is known as one of the most beautiful formulas in mathematics. It has e, a transcendental number, pi, a transcendental number, I, the square root of -1, 1, unity, and 0. So the additive identity. So this is known as one of the most beautiful formulas. If you have been online or seen The Simpsons, if you're a mathematician, I frequently get ads for products that have this formula on it. So it's kind of a big deal, and I want you to understand, you now know what it means and how it works. So e to the I pi, you'll see, I can't remember her name right now, but you'll see this formula. The Simpsons often put little mathematical equations in their show. So just a few things out there. It's also on my coffee cup if you've noticed that at school. But it is called Euler's equation, but Euler wasn't the original one to discover it, of course. But he was a great mathematician. So funny enough, that E, we do say it kind of came from his name, but this is called Euler's equation. Google online to get more information. Euler wasn't the first one that actually did it. So just something you might want some math trivia for you to know. Okay, back on topic. So why do we work with complex numbers? Addition and subtraction, not to break your heart, but it's not a whole lot easier. If you want to add complex numbers, you just add their real parts. So if I add z and w, I just take this whole product right here and add it to this whole product. I similarly take the modulus of z times sine, so take the imaginary part plus this imaginary part. Not a lot easier, done exactly like we would have done in college algebra, but multiplication way easier. I have the formulas right here, so you can go ahead and write them down, pause the video. I'm giving you the formulas. I hate to just give you formulas, I want to explain them. I'm not going to write out the second one on slides. If we were doing it in class, I would have you do it. If you have questions, let me know, but I'm about to explain why this first one works, and then you can use that to help you understand the division. So why does this work? Z times W, I take the moduli, and I multiply them. And then it looks like I add the angles, so cosine, and I take the sum of the angles, and then this is always the same, so cosine of that angle plus I sine of the same angle. So let's look at why that happens. Again, I do want to point out, I've mentioned this before, in mathematics, multiplication and addition are like best friends. They're often in the same equations together. So keep that in mind. Division and subtraction, they're best buds. They're often in the same equation together. Alright, so let me show you why this works now. So for multiplication, if you have two complex numbers, so here I have z and here I have w, or omega. And if we were in the classroom on a board, I'd have this written out. You know, I'd have this written out on the big board, but it wouldn't quite all fit. So what I have here is z times w. You take, what I'm doing is pretending that this is my a. So this might be my A1 and my A2. I'm just multiplying those, so I'm distributing. So I'm foiling this. So the modulus of z cosine of theta 1 times the modulus of w cosine of 2 is what I have here. And this product is going to be the same for each of them, so actually I'm just going to leave that out front. Okay, that would be my first. So I took the first from this times the first from this. Then what I didn't do FOIL in the order you're familiar with, because I knew that some of the products were going to have imaginary, to have I times them, but the last one won't, because it's I sine of theta 1 times I sine of theta 2. The I squareds will be -1, so that I'll have this product. You'll notice I color-coded this in green. We'll come back to that. For the imaginary parts, so the I sine of theta 1 times cosine of theta 2 will be this portion. The cosine of theta 1 times I sine of theta 2 will be this portion. And PowerPoint does not make this as nice as LaTeX. You'll see I put those yellow parentheses because that is all one term. And so that purple term is from finishing that distribution. All right, why am I discussing this? Well, we've been in trig for a while. We've talked about some formulas. If I hadn't ruined this already, I would have paused here and had tried to get you to think about, okay, what does this green part become? It's cosine of an angle, cosine of an angle, minus sine of an angle, sine of an angle. And yeah, you should be familiar with the sum formula for cosine. So that green portion is simply cosine of the sum of those angles. The purple portion is sine of the sum of those angles. Remember, cosine changes to a negative, whereas sine preserves the sign. So we actually can condense all that, and that explains why when you multiply two complex numbers, you take the product of their moduli and you add the angles. So theta 1 plus theta 2. Remember, whatever this angle is, it's the same thing over here. Division, if you think of it as the product, so z times 1 over w, what I would have you do in class is use when I talked about 1 over w would be the conjugate of w over w squared, the modulus of w squared. That is actually how you can work out this formula. It does take several steps, and it would have made this video quite a few minutes longer, so I left that out, but I encourage you to look at it yourself and investigate this. For division, you take the quotient, so you take the quotient of the moduli and you subtract the angle, so you find the difference of the two angles. Remember that that is not a commutative property, just like 3 minus 2 is not 2 minus 3. Keep that in mind. So I have put on the notes, I've put a couple problems on there. It says to find the product and the quotient of these two numbers. You can pause the video and try that yourself. I'm going to work through it now on this slide. Firstly, you need to write the numbers in polar form. You could, of course, multiply these out in rectangular form. 4 minus 4i times the square root of 3i plus 1. You would take 4 times the square root of 3i, you'd have a negative 4 square root of 3i, so I squareds, etc. What we want to do, though, is see the benefit of using polar form. So we are about to write these numbers in polar form first. Fortunately, we did the first one earlier, and then we're also going to look at the square root of 3 plus I. So earlier we wrote 4 minus 4i in polar form. Here you'll notice I have 4 root 2 times cosine of negative pi over 4 plus I sine of negative pi over 4. That was from earlier. Z2, because the real part is 1 and the imaginary part is the square root of 3, you might draw a reference triangle in the first quadrant which has a base of 1 and a height of the square root of 3. The hypotenuse obviously would be 2, because it's a 30, 60, 90 triangle, and the angle, the reference angle, would be 60 degrees or pi over 3. Once you have the numbers in polar form, now we want to use this new formula that we built. So to find the product, we take the product of the moduli, 4 square root of 2 and 2. The product of that gives me 8 square roots of 2. You'll take the sum of the angles. We'll have fractions here. Negative pi over 4 plus pi over 3. And remember, whatever you have here, it's the same for the second one as well. You just copy that. This is the same as negative 3 pi over 12 plus 4 pi over 12, which gives me pi over 12. This would be the product in polar form. And if I say leave in trigonometric form or leave in polar form, this is all you have to do. If you actually want to type this into a calculator, you could get A, the real part, and B, the imaginary part. But in trig form, this is all you have to do. For the division, you take 4 square roots of 2 divided by 2 square roots of 2, and you'll take the difference in the angles. This is negative 3 pi over 4 minus 4 pi over 3, which gives you negative 7 pi over 12. Remember, whatever angle you have there is the same angle here. In exponential form, this is even easier because of exponent rules. Then the product, you'll simply multiply just like you would in algebra if you had exponential functions. 4 times 2 gives you 8 square roots of 2. Add the angles. this is what we got. This is not what we got on the last slide. Ignore that for just a second. I'm going to make an edit. So there you go. These are the same angles from the last slide. So exponent rules, when you multiply exponential functions with the same base, you add the exponents. If you divide, then you subtract. So negative pi over 4 minus pi over 6 is the same value as what we would have had earlier. So powers of a complex number. If you had a complex number, z, expressed in trigonometric form, z squared would be the modulus squared times, and you'd have the sum, so cosine of theta plus its angle again, and I sine, that angle should be the same. So really that's cosine of 2 theta and sine of 2 theta. You could find z cubed by multiplying z times z squared. The product of the moduli would be given here. From the z squared times z, you'd add the angles so that you got cosine of 3 theta. So this leads me to wonder if there is a formula for z to the n. And there totally is. Powers of complex numbers in rectangular form can be very difficult, but in polar form, they're a piece of cake. So this is actually called De Moivre's theorem, and I think on your notes I had a place for you to write this in. For an integer n, z to a power n is equal to like so. So, and by the way, I should have put for a positive integer in here. Not that that doesn't work for negatives. Let me think about it. But for a positive integer n, that's when you'll be using De Moivre's formula, De Moivre's theorem. So keep that in mind. I will only ask you that for the positive powers. So really I meant for this to say for a positive integer n. Okay, as an example, earlier we looked at 4 minus 4i. Here it is in polar form. Same value we've looked at several times. If we take that number and raise it to the third degree, 4 squared is 2 raised to the third degree, because 4 times 4 times 4 is 64. You'll get another 2 from cubing the square root of 2, so that I have 128 square roots of 2, probably the hardest part. And then all you have to do to the angle is multiply by 3. Multiply by n. If the book wants this in rectangular form, you multiply this out on a calculator. So you'll take this to find a, and you'll take 128 square roots of 2 times sine of negative 3 pi over 4 to find b. I will often just ask you to leave it in trigonometric form. So if we were in class again, I would spend a little bit more time on this, but if we want roots of a complex number, this is actually what I was kind of getting at with earlier. So this would be, so earlier I talked about positive integer powers. Now we want to take roots, so like the square root, the cubed root. And so you'll notice I have 1 over n here. So the square root is 1/2, the cubed root is 1/3, and we're going to look at roots. This is really similar. It is. I know it might be intimidating at first, but it's really similar to De Moivre's formula. If you have a complex number, n here is a positive integer. I should have had that on the last slide. And then k is equal to, so k is like if you're a coder, it's your iteration. So k equals 0, 1, 2, up to n minus 1. We'll talk about that. I don't want that to be intimidating. Even if you mess that up, you can still get the answer most of the time. So 0, 1, 2, you stop at 1 less than n. And based on that formula, then we have z to the 1 over n. You will have, k tells you how many answers you have, so that's why you keep track of it. And each answer will have this form. It will be the modulus of z to the 1 over n. So you take the nth power of the modulus, piece of cake. Really similar to De Moivre's theorem, where instead here you have the modulus to the nth degree. Now we're taking the power of that, the root of that. And then instead of just multiplying by n, we want to divide theta by n. The problem is that because you're going backwards with that division, you could be missing answers. It's kind of like when we did, not exactly, but kind of like when we did trig equations and you had a multiple root, and so you always had to solve for all possible answers. That's what this 2 pi k is doing. So it's somewhat similar. So with the powers, we multiplied by n. Here you want to divide, but we have to have this extra 2 pi k to make sure we don't leave any answers out. Whatever this angle is, it's the same angle here. So that once you understand that a little bit better, remember these don't change. You won't have 30 degrees and 20 degrees here. That doesn't make any sense. Whatever angle here, it's repeated right here. So we're going to do an example. We're going to find the third roots of the complex number -1. You might not think of this, so this is a real number, but remember complex numbers, when I write complex numbers are the set of numbers containing real numbers, pure real numbers as well. So that's why these instructions look that way. To find the third roots, so I'm reminding you, so this is actually the same problem as solving the equation z cubed plus 1 equals 0. In college algebra, I talked about the fundamental theorem of algebra. It seemed pretty important at the time. For a cubic equation, so if this were x cubed plus 1, that has 3 complex solutions. And so if I just look at this, I can see, oh, this probably has one real solution, -1. But what would the others be? Well, that's what we're about to learn. You can actually find all 3 complex solutions for this. So to continue, first we want to write -1. So what I'm doing here is trying to solve for z. So if I subtract 1 from both sides, and then I'll take the cubed root of both sides. So -1 in polar form, we want to take the cubed root of -1, is simply the absolute value of -1, so 1. Cosine of, if you graph -1, remember it is on the negative x-axis, so the angle on the unit circle would be pi. So this would be the polar form for -1. I realize it looks a little messy, but using that, and we'll plug in the values for the formula. So we'll apply the formula. Because we want the cubed roots, n is 3 here. So this is z to the 1/3. Our z is -1, remember. So the modulus of z will be 1. K will be 0, 1, and 2. We stop 1 short of 3. Remember, if it's a cubed root, we want 3 answers, so that's why I have 3 values for k. K is like your program to keep making sure that you run the iterations. When you've let k equal 0, 1, and 2, you're done. Z sub 0, so that's representing z sub 0 for k equals 0. I'm going to plug in k equals 0. You'll notice z sub 0, the first solution, would be equal to 1 to the 1/3, which is 1, times cosine of, I use this theta, so pi, plus 2 pi 0 would be 0. So that's why I simply have the theta from -1 in polar form. So that's my theta over n, so pi over 3. Whatever this angle is, it's the same angle here. So that's all there is to it. We then try this for k equals 1. So I get another solution. Again, the modulus to the 1/3 will always be 1. So I'll have 1 out front for all of these. Cosine of pi plus 2 pi is 3 pi, and I'll have 3 pi over 3, which gives me pi. Z sub 2, I plug in 2 for k, so this part changes to 4 pi. Everything stays the same except for that. That simplifies to 5 pi over 3, and I'm done. If I were to accidentally do this again for another iteration, so for k equals 3, for instance, well, plug 3 in for k, you'll have pi plus 6 pi, so this would be 7 pi over 3. 7 pi over 3 is coterminal with pi over 3, so they're actually going to give you the exact same number. And so that's why even if you mess this k part up, all you're going to do is repeat work. You won't necessarily miss anything. So I'll take a little stress off your mind. I'm also going to teach you, this might seem intimidating at first. I want you to practice it a little bit more, but if you actually know some tricks, it's really a piece of cake. So let me show you what some kids might think these are shortcuts, but it's not necessarily a shortcut. It's just thinking about what you're doing here a little deeper here. So something I want you to notice, from your first answer to your second answer, that's pi over 3 to pi. What did you add there? You added 2 pi over 3. And that's important because this 2 pi k over n, because n is 3 here, you'll notice each time k goes up, you're going to be adding 2 pi divided by 3, so 2 pi over 3. Here you added 2 pi over 3, and how do you go from pi to 5 pi over 3? You add 2 pi over 3 again. If you were to accidentally plug in k equals 3, you would add 2 pi over 3, and you'd get an angle that was coterminal with pi over 3. So this repetition is because there are 2 pi radians in a circle. We are finding the cubed roots, so we're actually taking that entire unit circle and splitting it up into 3 slices of pi, you might think about it, that are 2 pi over 3 radians apart. If you were to go ahead and graph these, I'm going to show you how to graph these. So what I've done here is multiplied this out. I found a is 1/2 because I know cosine of pi over 3 is 1/2, sine of pi over 3, square root of 3 over 2, etc. So I get these three values, 1/2 plus the square root of 2 over square root of 3 over 2 times I. Now if we were in class and I had some time, I like to encourage you guys to actually take this value, this a plus ib, this number in rectangular form, and cube it. Now that takes some crafty algebra. You have to be pretty confident, but if you do so and you combine like terms and simplify it, you will get -1. And so that's kind of cool because you maybe didn't know that. I think I did some of that in college algebra, but most kids might not necessarily see that. And so this number cubed will solve this equation. So it's a solution to this equation. Similarly, you'll notice that because we had a complex number, its conjugate also was a solution. Here we had one pure real answer. If you were to graph these, so the way that I graph these is I opened up Desmos and I graphed the point, the ordered pair, 1/2 comma square root of 3 over 2. And that's actually this point right here. Desmos changes it to a decimal automatically. -1 comma 0 because this had 0 real part. Or I'm sorry, 0 for the imaginary part would be this point. And lastly, we have this. You'll notice complex conjugates are directly over each other, they're directly across from each other over the real axis. And what I want you to notice is these points are spaced exactly 2 pi over 3 radians apart. And again, that's because there are 2 pi radians in a circle. We are finding cubed roots, so the values, the solutions, will always be spaced identically apart. And that's actually a really cool trick. If you know that, it makes this work way less intimidating. So for the fifth roots of, and here you'll notice I've written it instead of the trig form, I've written an exponential form to begin with, but the modulus of this would be 32. So the fifth root of 32, I've plugged in 2. I need to do the work for the very first one. So pi over 2 plus 2 pi k all over 5. Because k would be 0 for the first one, I'll just have pi over 10 for that. So once you find the first angle, so you might pause the video and spend a little bit more time on that, but I found the modulus and I found the first angle. Well, because you're finding fifth roots, then each time, so once you find the first angle, you're going to be adding 2 pi over 5. Now because this has a denominator of 10, what I did is I thought, okay, 2 pi over 5 is the same as 4 pi over 10. So then I just added 4 pi over 10 each time. Pi over 10 plus 4 pi over 10 would be 5 pi over 10, same as pi over 2, 90 degrees. Add 4 pi over 10 again, 4 pi over 10 again, 4 pi over 10 again. If you accidentally did it again, that would be 21 pi over 10, which is coterminal to pi over 10. So you'll notice they're all spaced out like a perfect pentagon, a regular pentagon here, and that tells me I did my work right. So what I graphed is I used the x value 2 cosine of pi over 10 and the y value 2 sine of pi over 10 to graph these, and that's how I got this perfect regular pentagon. So these are a few ideas. I'm sorry this video was a little bit long. I've actually cut out a lot of material, so I might send another video out later with some more identities I think you guys would enjoy, and possibly some equations, because I really love this material. So I apologize for how long this is. Please split this up into two time segments to help you out there. I did post a homework assignment on Google Classroom, and there is a quiz coming your way on Thursday. Best of luck.